Welcome to This Explainer. I'm absolutely thrilled you're tuning in today because we're going to demystify the literal mathematical foundations of our physical and digital reality. We're going to explore how the universe, and, well, all the digital tools we build within it, are actually governed by pairs of contrasting ideas. Now, I know that might sound a little intimidating at first, but I promise you, once we break these concepts down, it's going to make total intuitive sense. Let's get right into it. So let's kick things off with a big, fundamental question. How do we actually describe the physical world? Just take a second and think about the space around you right now. Math and science weren't just stumbled upon. They were literally invented by humans as a language to understand, quantify, and predict the behavior of this chaotic, at least four-dimensional world we live in. And to write any language, you need a basic alphabet. Okay, so let's dive into the first letter of that mathematical alphabet, the scalar. A scalar is simply a physical quantity that's fully described by just a magnitude, basically a numerical value. It exists entirely independently of direction. You can think of a scalar as essentially zero-dimensional when it comes to direction. It just exists. It doesn't point anywhere. Like if you have a 5 cubic foot block of iron and you move it up, down, left, right, guess what? You still have a 5 cubic foot block of iron. The volume really doesn't care which way it's facing.
But now consider the flip side of that coin. Enter the vector. A vector requires both a magnitude and a precise spatial direction to be fully understood. For instance, just stating that you applied a force of 10 newtons to something, that's actually an incomplete physical description. I mean, think about it. That 10 newtons has a totally different effect if it's pushing a book up against gravity, pulling it down, or sliding it sideways across your desk. The direction completely changes the physical outcome.
So here's our roadmap for today. We'll start with magnitude versus direction, meet the kinematic twins, break down the dot product for measuring similarity, and the cross product for measuring difference, before finally wrapping up with vectors in the real world. Section 1. Magnitude versus direction. Check out how these physical properties pair up. A really common point of confusion is mass versus weight. Mass is a scalar. It's just how much matter is in an object, like, say, 50 kilograms. And that's 50 kilograms no matter where you are in the universe. But weight? Weight is a vector. It's the actual force of gravity pulling that mass downward. Grounding this abstract math in reality makes it so much easier to digest, right? Like, you don't feel 20 degrees Celsius in a specific direction, but you absolutely feel 10 newtons of force pushing you backward. And this complexity is exactly why vectors exist in the first place. In our multidimensional world, the physical state of a system is just way too complex to be summarized by a single number. By using vectors, we can take a chaotic, complicated 3D problem and break it down into simpler, independent, one-dimensional components. The x, y, and z axes. It's basically the ultimate divide-and-conquer strategy for physics. Section 2, the kinematic twins. This brilliantly illustrates the duality of motion, distance, and displacement. Imagine you're out for a run around a circular park. Distance is the scalar. It's tracking every single step you take. By the time you finish your lap, you might have covered a pretty significant distance, maybe a few miles. But displacement? That's the vector. It only cares about your starting position and your final position. If you finish exactly where you started, your displacement is literally zero. You moved miles, but mathematically speaking, you went absolutely nowhere. The exact same rule applies to how fast you're going. Speed is our scalar. It's kind of like just reading the speedometer on your dashboard. Velocity, on the other hand, is the vector. It's your speed plus your heading. If you're driving a car at a constant 60 kilometers per hour on a winding road, your speed never changes. But because your direction is shifting with every single turn of the steering wheel, your velocity is constantly changing. And here's the kicker. A changing velocity vector means you're actually accelerating. Yep, because acceleration is a vector too. Section 3, dot product, measuring similarity. Now, let's forget about intimidating formulas for a second and just focus purely on the visual intuition here. The dot product measures the similarity between two vectors. We're essentially asking the math, hey, how much do these two arrows overlap? Or how much of vector A is pushing in the exact same direction as vector B? And this introduces a highly important number to our math, 0. If two vectors are perfectly orthogonal, which is just a fancy way of saying they're perfectly perpendicular to one another, like the corner of a square, their dot product returns a single number, 0. Why? Well, because they share absolutely no overlap, 0 similarity. It makes sense, right? A force pushing straight up does literally 0 work, moving an object straight horizontally. Section 4, cross product, Measuring difference. Notice how perfectly these two multiplication methods complement each other. The dot product gives us a scalar number, it works in any dimension, and it measures similarity. But the cross product? That's kind of the wild sibling. It spits out a brand new vector, it strictly only works in 3D space, and it measures difference, basically how far apart the vectors are pointing. So what is the cross product actually doing behind the scenes? Well, it's measuring the area spanned by two vectors. It accumulates these 6 cross interactions between the different dimensions, like the x of one vector interacting with the y of another. And the result? A brand new third vector that plays favorites with neither of the original directions. It is totally 100% perpendicular to the original two. Okay, I'm going to break the fourth wall here for a second. I want you to physically hold up your right hand right now to learn the right hand rule. Seriously, do it with me. Point your index finger straight forward. That's vector A. Now point your middle finger off to the left. That's vector B. Got it? Now stick your thumb straight up. Your thumb is pointing in the exact direction of the cross product. Since there are 2 ways to be perpendicular to a flat plane, up or down, we use this standard convention to resolve the ambiguity. Pretty cool, right? Section 5, Vectors in the Real World. Now, engineers actually classify vectors based on how they're allowed to move within a mathematical model. For example, we've got the sliding vector. This brings up something called the principle of transmissibility, which is awesome. It states that as long as you stay on the exact same line of action, pushing a broken down car from the rear bumper has the exact same external effect as tying a rope and pulling it from the front hitch. The overall motion of the car is completely identical. And the real-world applications for this, they're literally everywhere. When you fly, aviation navigation relies entirely on combining airspeed and wind vectors so you actually reach your destination. Fluid dynamics uses vector fields to design safer airplane wings. Every single 3D video game you play uses vector cross products to render light rays bouncing off surfaces. Heck, even the AI on your phone encodes your data as high-dimensional vectors, using the dot product to find the distance or similarity between your behaviors, just to recommend your next video. Ultimately, this all leaves us with a final thought. Everything, from the structural integrity of the bridges you drive over to the algorithms predicting your very next purchase, relies on this beautiful dance between magnitude and direction, between the scalar and the vector. Thank you so much for joining me in this explainer. I really hope you leave today looking a little more closely at the forces and directions moving the world around you. So, I'll leave you with this. What invisible vectors are shaping your direction right now? Keep learning, and I'll catch you next time.